The next in line, I believe, is Alberto Ledesma with a lecture, including unsaturated soil concepts in undergraduate courses, the UPC experience. Thank you.
My name is Alberto Ledesma, and the rest of the authors, we are all involved in teaching soil mechanics at undergraduate level, also at master level, but I will deal with the undergraduate level in this presentation. This is the outline of the paper, the introduction first, then historical perspective, the UPC experience in this task, and some concluding remarks. About the introduction, this presentation is about content of the subject. We are expected to teach the state of the art of our discipline. But if you have a look at some information provided by the accreditation boards, for instance, ABET from US, they say an engineer should have ability to, there's a list of skills, apply math, science, engineering, design and conduct experiments, design a system, work in a team, solve engineering problems, ethics, ability to communicate, impact in global society, lifelong learning, knowledge of contemporary issues, techniques and skills for engineering practice. So nothing is said about being at the limit of the knowledge, at the wedge of the knowledge. Maybe when they say lifelong learning refers to that. An engineer should be able to learn continuously because technology is changing, science is changing. But it seems that these accreditation bodies are worried about the skills. The engineer has to communicate well, but they are not worried about the knowledge, what we teach. And this is because they trust universities in teaching the recent developments in each field. But they don't check that in detail. They assume that professors, they are able to teach the state of the art in each discipline. But nobody controls that in detail, I think. Now, having a look at the historical perspective, these are two seminal books, you know, the one from Terzaghi, the other one from Donald Taylor back in 1940s. They included a chapter on capillary forces, on capillarity. The book from Terzaghi, I didn't find any reference to compaction. The book by Taylor, there is a limited reference to compaction at the end of the book in a chapter about dams, but not too much, in fact. Well, and many textbooks from 1960s to 2000, didn't consider capillarity or unsaturated conditions or even compaction. The book by Lambe and Whitman, which has been a reference book in many universities for many years, considers compaction at the end of the book, a small section. And the book by Atkinson, the first books, they didn't say anything about unsaturated conditions. Well, the latest editions, they include a chapter on that. However, in some countries, some textbooks did include concepts on unsaturated conditions already. Back in 1975 in Spain or 1974 in Mexico. They were written in Spanish. So it seems that the content depends on the country, which is it's a bit strange. Now there are many books on saturated soils, but basically they are research-oriented. So you're right that there is a need for incorporating these new topics into undergraduate courses. Maybe the book by Jean-Louis Briot is a sort of textbook trying to unify saturated and unsaturated conditions. So this is the historical perspective. Now our experience. The context is that we are a relatively young civil engineering school that was founded 50 years ago. And the research from the beginning in geotechnics was linked to unsaturated soils. In fact, the first journal paper in 1980 from Abed and Alonso was about consolidation of unsaturated soils. And we think that research and teaching should be connected to some extent. So we try to incorporate all this research on unsaturated soils into not only in master's courses, but also in undergraduate courses. And this is the framework. We have a civil engineering degree, which is quite general, has a bachelor diploma plus a master engineering diploma. So considering now the bachelor and undergraduate courses, we have these 4 subjects. So geology, year 1, or it's applied geology, in fact, groundwater hydrology, geotechnics, which is in fact soil mechanics, and geotechnical application at year 4. one credit means about 10 hours of classes, so face-to-face classes. So let's focus on this subject, on the techniques, which is in fact soil mechanics. And this is the syllabus. You see a number which is, this number here, 2 means number of hours, T means theory, classical class, or active or passive, classical class in a classroom. Then P means problems or exercises, and L means laboratory sessions. So you have the syllabus of the subject, about 60 hours. We start with the soil characterization, classification. This is the standard units. Stresses and strains, experimental behavior, unsaturated soils and compaction. This is strength behavior with camp clay, flow, seepage forces, and consolidation theory at the end. Although they know what does consolidation mean here in these units here. And in addition to that, we have the laboratory sessions, 3 laboratory sessions, about 2-3 hours each one. And focusing on the unsaturated content, in Unit 1, we start presenting unsaturated soils in a natural manner. So soil is a mixture of 3 phases: solid particles, liquid phase, and gas phase, typically air. So we try to present the material in this way, because this is the common situation in Mediterranean countries. And for instance, we try to include, when teaching Atterberg limits, not only teaching the liquid limit or plastic limit, which is the usual way, but we also include the shrinkage limit, which is maybe important in this condition, in this context. And we also take into account these unsaturated conditions in the laboratory session, in the first session, where the students have to identify materials to mix with water, different amount of water. So that was Unit 1. In Unit 4 is devoted to unsaturated conditions, saturated soils, and we try to present the concept of capillarity first, which is, well understood, this is a simple experiment, suction, retention curve, and compaction, Proctor test, and so on, relative compaction with microstructure, and then also strength and permeability of compacted soils. And in session 2 of the laboratory, we try to prepare, we have a small Proctor test. It's the same idea, but using a small mold just to speed up the process. And we try to reproduce a collapse of the sample when wetting, which is something that happens quite often in southern countries, because if we have a dry weather, then compaction many times is carried out on the dry side. So we may have collapse when we have rainfall. And finally, in Unit 5, we have to explain, obviously we explain saturated conditions, but we have to include, at least qualitatively, the effect of unsaturation on strength and stiffness. So here you have some figures taken from the Unit 4, dealing of unsaturated and compacted soils. Figure A, you see the typical experiment of capiillary rise. Figure B is the meniscus, again, this surface tension effect, difference between air pressure and water pressure. Water pressure is less than air pressure. This is 0, this is negative. And figure C refers to the effect of suction of the meniscus. Because of this surface tension, we have these additional forces in red that you have to add to the contact forces and mechanical forces in yellow. And finally, the retention curve, considering the drying and the wetting path. So these concepts are included in this unit, in Unit 4. And finally, to conclude, we think that we have the responsibility of teaching the state-of-the-art concepts. And because nobody will check that. Even the accreditation boards or any external bodies checking what we teach, they are not experts on geotechnics. Typically, there will be a civil engineer that will check the global view of the global aspect of the course. But we have the responsibility of teaching the latest concepts. This is on the one hand. On the other hand, associated soil mechanics is mature enough as to be incorporated in undergraduate courses. At least at the quantitative level, and we have got an example from Professor Tarantino. It's possible to do that, including water pressure above water table, the concept of suction, water retention properties, and the effect of suction, soil permeability, soil stiffness, and soil strength. And finally, compaction is a soil mechanics concept, so it's scientifically well defined nowadays. So an exclusive technological approach to compaction, which is the tradition, is incomplete. So compaction is not just a soil improvement technique, it's more than that. So this is why I think we should include that in the soil mechanics core material. And that's all for me. Thank you very much for your attention.
Thank you very much. As I said before, we have another presentation because these are all tied together before the discussion. And so we have teaching unsaturated soils and related soil mechanics in a South African context.
All right, so when Charles and I saw that one of the key themes for the conference was unsaturated soils, we thought it was a nice opportunity for us to look at our local context and see what are the perspectives of academics and practitioners to teaching and using unsaturated soil mechanics principles. And so I'll be presenting our results on that. So in South Africa, our context actually dictates that we have a lot of unsaturated soils. And the reasons for this is, number one, our climate. 85% of the country is water deficient, which means that there's more evapotranspiration than precipitation. And this results in deep water tables and residual soils, all of which we know have unsaturated soil regimes. We then have, in the context of a lot of the geotechnical work, there are 5 key problem soils that we have in our region. And 3 of these are expansive clays, collapsible sands, and dolomites or sinkholes. And these problems are only problems because you have changes in water content. If you didn't have a change in water content, your expansive clay would just be a clay. It wouldn't expand and shrink. So an appreciation of unsaturated soil mechanics and changes in moisture are required to actually fully understand problem soils. And the third is, as I mentioned in my presentation yesterday, in our geotechnical community is involved in a lot of mining work, specifically in the design of tailings storage facilities. And these, the deposition of these is a slurry, and this creates a saturated, unsaturated regime in these embankment dams. So we looked at the soil mechanics perceptions, and we did a survey with academics and with some industry professionals. And I'll go through those briefly. So for the academics, we sent a survey to academics in South Africa and in Namibia, and we asked them what is covered in their curricula on unsaturated soil mechanics, what do they see as the value in their local context, where do they think that content could be added, and what are the challenges. And combined with the survey responses and Charles and my own experience at various institutions in the region, this covers about 5 civil engineering programs. And I'm briefly going to look at just what they cover and the challenges noted. So in the current curriculum, none of the universities cover anything explicitly about unsaturated soil mechanics in the undergraduate courses. So what's typical in our area is that we have a 4-year undergraduate program, and then the postgraduate program will be a specialist 2-year master's program for geotechnical engineering. So it's a 4 and then a 2. Generally, most people will cover concepts around the problem soils that I mentioned, usually in a geology or an engineering geology course, but these may not be explicitly linked to anything about unsaturated soils. And then at the postgraduate or graduate level, at one institution there was a 1-day course on unsaturated soil mechanics, and at another institution, concepts around unsaturated seepage were included in guest lectures in a course, but that was the extent of the exposure. And the challenges noted very similar to what Jorge mentioned yesterday about bringing in geosynthetics in the curriculum, limited time in the curriculum, limited instructor knowledge on the topic, I think, like the presentations have said before me, the non-experts teaching it, the time to prepare the required material in addition to what's already being taught, and then also importantly, limited capacity of the students to expand in this new area of knowledge, and a desire to first get the basics of soil mechanics right before exposing them to this other realm of soil mechanics. And then from the industry perspective, so we sent just a targeted email to prominent geotechnical engineers, and we were asked them to answer 2 open-ended questions. Which unsaturated soil mechanics principles do they use in practice? And which principles do they feel should be taught at university? And then we asked them to expand if they do use the principles, how and where, and if not, why not? So we sent 30 emails and we got 3 responses. We clearly don't have the influence that Jorge has with his very, very high response rate. We will try again maybe in 20 years. And I'm going to briefly look at their responses to what they were using, and the related challenges that they highlighted on the if not, why not. So where people noted that they were using unsaturated soil mechanics principles was in one response said in the design of evaporative covers, so looking at permeability and seepage principles. There was some comment on an appreciation of the role that suction plays in keeping slopes up. So this is that kind of inherent thing that we know that suction causes some apparent cohesion, which is causing the slopes to stand up, but we don't always have the ability to quantify it. And then some appreciation also of the rainfall-induced instability of unsaturated slopes. So the slopes are standing up because they are unsaturated, and then when we have rainfall, the moisture is contributing to some failures of those slopes. And the challenges that these practitioners noted was that it is unconservative to rely on soil suction. That was the first one that came up. This is not new. I think Fredland wrote a lot about this in some papers on myths and challenges to unsaturated soil mechanics implementation. And the comments were that practitioners are scared that the conditions can or will change with time or are influenced by the environment. And saturated soil parameters are conservative, so therefore they're going to stick with that. Then other challenges was the difficulty in establishing the in situ moisture and suction regime, and related to this is very limited access to laboratory testing. And in South Africa, we only have one university laboratory that does full soil water retention curve testing, and none of the commercial labs do this. And obviously we know you can, if you want, use the particle size distribution to get an indication of what that soil water retention curve is going to be, but there's very limited knowledge in the industry on how to do that. So what Charles and I did is we put together a simple little case study mostly for ourselves to illustrate the capabilities of unsaturated soil mechanics and what the implications are when we compare the results to a saturated only to saturated, unsaturated behavior. And we thought that this is something that can be used for mostly an effective purpose, to excite and to motivate and to just illustrate what is possible. And we looked at 3 case studies, so a seepage, a stability analysis, and seepage-induced instability. And I'm briefly going to look at the results from the first 2. So for the seepage, we looked at this very simple uniform material slope. It has a constant head boundary condition on the one side and ponded water on the other side. This is done in rock science. This is basically just one of their tutorials that I just took and then adapted. And we modeled 3 different materials, a sand, a silt, and a tailings, and this is the relative permeability of those materials, so it's very similar shape to the soil water retention curves. And we compared the saturated only flow, so assuming completely saturated, completely dry, to a saturated, unsaturated regime. And we found that there is a seepage increase, obviously, when we have saturated, unsaturated flow. And this is much more prominent for finer materials, as the fine material holds on to its water for much longer. As you have suction, so you have more flow in the unsaturated regime. So from 2% to 10%. And only a nominal increase in the phreatic surface was noted. Thank you. So for the suction, for the stability analysis, we looked at either using no strength in the unsaturated zone, a capped strength in the unsaturated zone, or a shear strength increase equal to the angle of friction in the unsaturated zone. And one of the comments that was made in the previous presentation was that it's excessively unconservative if we ignore the cohesion. And what we were actually found was very interesting was that the increase in the factor of safety was rather nominal. So from 1.45 to about 1.52 if you take the unsaturated shear strength into comparison. Granted, this is for this very specific example, but we did find that quite surprising. Okay, so our conclusions were that at the undergraduate level, focus should be on development of core soil mechanics knowledge, particularly in our context. Conceptual understanding of unsaturated soil behavior at undergraduate level is required, and students should be able to give a qualitative description of suction and the impact on soil behavior, perhaps using some of those examples that we showed. And the detailed presentation of the principles, including in equations or state variables, and the debate about which ones, if bishops or the two state variables, is for further study. And then we have some remarks, and I'll just leave those there in the three different realms on what are the qualitative understandings required in seepage, strength, and volume change. And in the interest of time, I'll just leave that there. Thank you.
So, in the order that we have here, next is Katia Bicalho. Well, she's already here, with a contribution on why unsaturated soil mechanics is relevant to civil engineers. I invite everybody to take a seat, and I invite Katia to start. Thank you.
Okay, good morning, everyone. I'm going to present like 8 slides. It's about a paper that's why unsaturated soil mechanics is relevant to civil engineer. Actually, it's not a question. I agree that's relevant. And also for the why you should, I think that most of the people here, they agree that we have learned a lot by studying unsaturated soils, and then it's necessary to teach in undergraduate students. It's important to remember that unsaturated soil is not a new soil, it's only unsaturated condition that's common in natural geological formation and also in man-made earth construction. That's the reason because we have discussed about the compaction soils. And also the unsaturated soil mechanics, it's the soil mechanics, but with some concepts that we have already learned. It's relevant for geoengineer because most of the infrastructure are constructed about the groundwater table, and also compact soils, unsaturated compact soils are widely used in civil engineer work. And Professor Houston, she mentioned about some key points that we could introduce in unsaturated soil mechanical costs. She mentioned about the unsaturated stress state that should be evaluated considering the 2 stress variables, and also suction should not be considered 0, and also shear strength and volume change in unsaturated soils are dependent on soil suction confining stress, and also in the site investigation test must account for both of stress variables, and also water followed the Darcy law but we don't have a constant. It's a function, it's a non-linear function of the water content, and also the unsaturated response require testing, good testing, and simulations, data, and their interpretation. The interpretation is something that I think that all the knowledge that we have in unsaturated soil conditions is going to help a lot. And also, I add just a small comment that also remember that the hydraulic conductive function, we know that in saturated soil has a wide range, and also with there is spatial variation, high stress in the function should also be relevant for the for us to learn a little bit about the unsaturated soils. And so in the paper, I wrote that the main goals are to emphasize the benefits of the introduce the fundamentals of unsaturated soil mechanics to undergraduate course, to explore possible application of unsaturated soil mechanics in some geotechnical problems or challenge, and to motivate geotechnical engineer and the students, structure and students, to read some literature about unsaturated soil mechanics. And actually, for example, this is my first slide. Water plays an active role in geotechnical engineering. And, for example, most of the process involves soil and water interaction in the field. It's during to have the unsaturated conditions. And also, I include here, maybe this figure, it's in some old books, so the Professor Tarantino also present some nice examples that about the importance of the relationship between the negative pore water pressure and also the some water count or degree of saturation. We always know that, for example, this is a very simple curve. It's a limit curve in a drain path. And in the field, we do have some dynamic and variability of the soil water system. And so, for example, just showing a figure that we know that in the field, the relationship between the suction and the water count may not be in exactly when we are measuring the lab, where we have a very controlled situation. And also the hydraulic conductivity is going to be different. And in the paper, I present very simple way with some examples about the soil profile, also the state variables and shear strength, and also unsaturated compact soils in civil engineering structure. Actually, it's one paragraph. Then yesterday, Professor Marina, she presented a wonderful lecture about how unsaturated soils are important to engineer, and also we can use some knowledge from unsaturated. If you draw the lines, that was I was talking, that for example, when we draw the compaction curve, remember that this compaction curve is only for soil with some plasticity, because if you have, for example, sands, clean sands without fine, we are not able to have this curve. But if you have this curve, for example, helps a lot, because the people in the fields, they used to increase now they are not using this standard. For example, we learn a lot, and many of the correlations about this maximum, this line, the maximum line, is related to the plasticity limit. That's also are not good parameter or properties index, because the variability is not easy to measure, but it's better than do all the curve. It's helping us. And when we are doing the compaction curve, it's important to remember that this is experimental data. So if you could also present the compaction curve with the saturation lines, it's helped us even check if some points during the testing was not did in the right way. Also, the stability analysis that we have present to very nice presentation about the stability analysis. So I am going to concentrate in the talking about the ground profile, because that's also something that even the undergraduate student, they are used to have the CPT data, maybe in Brazil more, the SPT data. But for example, I like very much this figure. This figure is a conceptual model, is qualitative way, so I'm not seeing any numbers, but also they show us, for example, that's actually the development of the suction during the time period. I think that's very nice, because often when the people do the ground investigation, site investigation, they forget that the groundwater table is not a fixed point. And also they forget that this site that they are going to use during the construction, the water count is going to change. And also the things show some, even some vegetation. And we know that's the influence of the vegetation in the development of suction. We don't need to explain that to the students, but maybe they are more familiar with some measure by using the CPT-KC. Okay, so that's the two figures that I want to show. That's the CPT-KC data. That's the measure by the people from Australia. And that's something important when we are using some data. Marina mentioned yesterday about we have to show the quantitative figure. And that figure shows us that we do have some significant change in the CPT-KC data during the dry and wetting season. It's not easy to get good measurement but in this way, in this group, they were very concerned about that. For example, even they have two different contractors for getting two different data, CPT data. And then we can see, I'm using this active zone, but then we see that, for example, in the wetting season, this suction decrease, and then the infiltration become important. We have the precipitation or maybe some runoff. And also during the dry season, the evaporation. And we see that, for example, the difference in the KC measurement was significant. Here, it's a measurement that's being done in Brazil. It's in São Paulo, so it's not a very dry region. And you can see also, in this way, it's showing by water count. It's also nice for the students when they see the water count and also they see the suction, because if they increase the water count, it means that it decrease the suction. And in that case also, it's something nice for, they have some ideas, the need for to know something about the unsaturated soils, because, for example, the first idea of some of my students, when I show that figure, they want to do some, how much the suction change in that figure due to the change of the season. But it's not that way that we should do, because it's not the range of the suction, but the range of the water count, but also the relative variation of the suction with the water count. And then show also the active zone. You can see that the name is not a good name, in my opinion, because, for example, if you plot KC or if you plot suction, the depth is different. So I want to thank everyone for the attention and also the The academic support I have received from my university, Federal University of Espírito Santo, and also I have get some support from the Brazilian agents that's called CNPq and CAPES. Thank you very much for your attention.
Good question, if you have it. Nobody? Okay. If not, thank you, Katja. And next in the lineup, teaching unsaturated soil mechanics through rammed earth. Cristina Vulpe, floor is yours.
Thank you, everybody. So I'm going to talk a little bit about how I'm teaching unsaturated soil mechanics in environmental geotechnics at the University of Western Australia. This is at least the third geotechnical engineering unit that students take at UWA. So when they come over to this unit, they have already done at least 2 other units. And this is an optional unit. So how I'm teaching it, I'm assuming the students are well prepared to come over to my class, and they are also extremely interested in geotechnical engineering when they are coming over to my class. So I'm not taking them from first principles at all. They have to come in prepared. If they don't come in prepared, they are in a world of trouble. And I have developed this part of the course on teaching unsaturated soil mechanics using some of the work that Christopher Beckett has done. So he has done some research on unsaturated soil mechanics on rammed earth, and it was a very elegant, simple solution that he has proposed. And I thought, well, this would be actually excellent to introduce for my students as an introduction to unsaturated soil mechanics. So although I have developed this part of the unit at UWA, and Chris is over at the University of Edinburgh, and you're wondering why is he there? He's there simply because I have asked him quite a lot of questions and I have used quite a lot of his knowledge in developing this course. So when we think about environmental geotechnics and the way we are teaching it, it's usually we are kind of associating environmental geotechnics with containment, mitigation, remediation, reduce, alleviate. So they are kind of like we're kind of trying to stop fires. And I was like, well, as engineers, we don't only stop fires, we also have proactive, positive environmental solutions. So when I was thinking of teaching unsaturated soil mechanics, I was like, okay, I can do it through geothermal energy or rammed earth structures. And I was like, well, rammed earth structure sounds good, and I'll show you why in a second. I'm coming from Western Australia. It's extremely dry over there, so it makes a lot of sense. So looking at rammed earth structures, basically they have almost zero carbon footprint, they have natural hydrothermal regulation of the building, and they also provide circular economy. Essentially, when you want to demolish that building, you're demolishing the soil that was already available on site, so you're returning the soil to the location, to its natural condition. I'm teaching using a variety of case studies in my unit. So the students that are coming over, they are in the last year of study. Usually they are also in their last semester of study. So they are one step away from going into industry. So I'm teaching them the theory, but then we are also putting it in practice during the workshops in the classes. And I'm wanting them to think that they are going to design a rammed earth wall in the Margaret River area in Western Australia. It's a very well-known area for Western Australians and Australians in general. So students are very well prepared when they are coming over. They can visualize where they will be building this rammed earth in the nice winery area. Also, case studies, I believe that they help students to be confident in tailoring specific engineering solutions to realistic real-life problems. It also gives them an indication that there's not a single solution. So when you as an engineer, you have to think. And if you have 30 engineers, they might come up with 30 different engineering solutions, and they could all be very correct. So this is something that I want to introduce in the class as well. It's not just one thing that you do, and it does the right way. There are many right ways to go about it. You just have to know the theory and then put it into practice properly. And Ram dirt, basically, it's, in terms for a geotechnical engineer, it's a highly compacted, unsaturated soil. I know that we have quite a lot of debate over this topic quite earlier, so I'm going in prepared. But this is basically what ram dirt is. It's a highly uncompacted, unsaturated soil. So it makes sense to teach it to an introductory soil mechanics, unsaturated soil mechanics course. There are lots of ram dirt buildings around the world that have lasted over the millennia, so there's no point in not actually thinking that these are actually proper buildings that you can actually teach students how to design. And in order to do that, in the environmental geotechnics engineering course, I have 2 weeks of teaching, 2 sets of lectures and 2 sets of workshops. And I'm dividing that into 2 parts. One is basically where I want them to remember the basics. And that's where they do their particle size distributions, they are looking at plasticity limit, liquid limit, their shrinkage limits, they are doing the modified Proctor test. So basically I want them to remember what has been taught to them at least a year before in the basic geomechanics course that they have been taught. And this also helps with something else. One is helps them to remember what they learned in the past, but also it helps them understand that what they have learned in the past is actually very useful and is very practicable. So it's not just something, it's not just pure theory that they are learning and it's just going somewhere in a shelf and then they go into the real life and this stuff is no longer useful. So this is extremely important for them. Simple tests, simple laboratory tests are extremely important in their careers if they are going to become geotechnical engineers. So asking for a particle size distribution curve and understanding it is very, very important for them. Understanding shrinkage limits are extremely important, and they are very important for render design. So I want them to go back and remember that part, and then we come to class, and then we have to think about how they are going to design this rammed structure in the Margaret River area. And they are going to have to think about whether that soil is suitable for designing a rammed structure, and whether the natural soil, if it's available and it's suitable or not, then whether they can actually, do they require lime or cement in order to stabilize it or not? So these are things that I want the students to think about during the class. And then the following week, they are going into into mid-year geotechnical engineering problems. So that's where they start learning about matrix sections, they are starting learning about soil water retention curves, and they are exploring the relationship between soil suction and water content. And that is a very, very critical tool for characterizing unsaturated soil. And then we're also looking at the effect of suction on strength. And I want them to understand that suction is a very, very important component in unsaturated soil mechanics. And in order to do that, in order for them to get an understanding in such a short span of time to understand unsaturated soil mechanics and to understand suction, I have used Chris's extended and linearized Morculum framework that he has developed during his research, and he has published in Geotechnique. And I thought, well, if it's good for Geotechnique, then it's good for my students. And then I want them also to understand plots. I want them to understand what the soil water retention curve looks like, and I want them to be able to pick up data from there and basically how they would be doing it in a consultancy firm. If they go to work in consultancy and they need to build a rammed structure, they would most likely have to go to a laboratory and ask for a soil water retention curve, just to understand, how is suction changing with evolving degree of saturation. Because for rammed structures, moisture is basically the Achilles heel. And as moisture is increasing, the suction is decreasing. So basically, that's where people can become relatively uncomfortable with the idea of rammed structures, and they'll be like, well, we actually go with brick. Let's forget about the rammed structures. That's a bit too niche for us. We'll just build it with brick, and we don't really care about anything anymore. But I want them to actually understand, how does suction affect strength of soil? So we do that very simply using Chris's research. And I'm talking a bit more about this in the paper that we have put together for this conference. But basically, I want them to understand, how is suction affecting strength, and how can you use that in your advantage, especially if you want to design a rammed structure. So in conclusion, unsaturated soil mechanics is taught as an optional unit for students that in the School of Engineering at the University of Western Australia. This is at least the third geotechnical engineering unit that they are taking. I'm teaching this in flipped mode, so the lectures are already available for them online a week prior to the workshop. So when they come to my workshop, they have to already learn the theory so that we can put it together in practice during the workshop. And then I want them to revisit basic soil mechanics aspects in order for them to refresh their memory on basic soil mechanics, but also understand that that's something that's really useful for them to use in practice. And also I want them to learn how suction is the key mechanism behind strength and strength gain, and how that can be modeled according to an extended Moore-Coulomb failure envelope. Thank you.
Much, and we have time for a couple of questions from the audience.
Don't ask me about compaction.
Alessandro?
Just a curiosity, because you mentioned the problem of the water. I'm not talking the water that may affect the resistance. Yeah. I'm not talking about the fundamentals, but you said that you are working on projects that have been carried out by industry.
That I'm working with projects with industry?
Yeah.
Myself? Yeah. Most of my research.
Even the students are working on projects that are simulating, mimicking, or taken directly from industry? No, or you are just introducing?
So for the unsaturated soil mechanics, I'm introducing...
Or the rammed earth. So are you applying the rammed earth to some kind of construction taken from industry, or just teaching the fundamentals?
Both.
Right. So my curiosity is that how you and/or industry is dealing with the water?
In Perth, quite easily, because it doesn't rain. In Perth, it's very easy because it doesn't rain. How we deal with the water in Perth, it doesn't rain.
Right.
This is why I said that rammed earth structures are really suitable for Western Australia. It's so dry for such a long part of the year that they don't really have problems. Oh, and actually I had the last slide here. So what you see on the left-hand side, that is the primary school made of rammed earth in Perth. And that there is the building, a rammed earth building in the Margaret River area. There are lots of wineries in Margaret River that are made of rammed earth. There are quite a few people, environmentally friendly thinking people, that are having their houses made of rammed earth, but also public buildings are made of rammed earth. Yeah.
Last one.
So this is a series of lectures within an unsaturated soil course, that was one.
So
one
what
question,
I'm teaching.
But my second question is about delivery, and I noticed that you said that this was a flipped class.
Yeah.
And I wanted if you could comment on that.
Okay, thank you. So I'm teaching 2 weeks of unsaturated soil mechanics within the environmental geotechnics unit. I have 12 weeks of teaching. The other ones are dedicated to stability against static and cyclic liquefaction, stability against cyclic circular failures, translational failures, contaminant transport, and I'm doing that using tailing storage facilities, because there are a lot of tailing storage facilities in Australia, and also when I'm talking about contaminant transport, then I'm talking about landfills, because we have thousands of those as well. Yeah. Yeah.
Your methods of teaching?
Yeah, my method of teaching is flipped mode. So the lectures are pre-recorded with a lot of available materials, additional materials if students are really interested in the topic, and they have 1 week to go through that material in their spare time, and then when they come to the workshop, that's when we get cracking. Yeah.
Thank you very much. Okay, we move on to the next presentation. Thank you very much again.
Thank you.
And the next one, it's integrating soil suction in geotechnical education. a case study on partially saturated slope stability analysis is in Sweden. Abed and Karstunen, sorry for the pronunciation.
Good afternoon, everyone. In this talk, I will be sharing some of our experience in Chalmers University in Sweden with integrating soil suction in geotechnical education. And for that, I will start with a very short introduction to the course where we offered the introduction to partially saturated behavior as part of other materials. Then I will be focusing just on one specific coursework, which in relation to that topic, to the partially saturated behavior, and then I will be talking about the methodology used and key findings from the students' analysis, and then some educational impact, and I conclude with some remarks and future improvement. Now, in 2022, we introduced a new course at Chalmers University. It's called Contemporary Topics in Geomechanics, and it has the code ACE 230. And it is offered to the 5th year's master's students in civil engineering. The main motive behind the course was that we want to equip the students with advanced knowledge relates to some current topic, contemporary topics, to be able to tackle new challenges related to climate change and sustainability. Now, the course has 3 main parts. The first part relates to introduction to soil mechanics for partially saturated soil with main focus on slope stability. And then we have other parts relate to ground improvement techniques. The first part is lectured by me, the second part mainly by Professor Mina Karstunen here. And then we have a relatively smaller part related to soil dynamics with focus on high-speed railways and renewable energy projects. The delivery methods is just we have a combination of lecture contact session with the students, and then we have tutorials, some computer sessions. But the main thing about this course that it is a project-based course, that the final evaluation of the students will be based just on their performance in the assigned coursework. So we have one coursework relates to partially saturated behavior, other one relates to ground improvement, and then relatively smaller assignment relates to soil dynamic. However, this talk will only focus on the coursework relates to partially saturated soil. For the partially saturated soil coursework, the design of this coursework was done in the, using so-called constructive alignments. So we want to, the learning activities should be, and teaching activities should be serving the intended learning outcomes for this part of the course. The core concept covered in this part is unsaturated soil characterization. Then we have introduction to stress measures as used in unsaturated soil. So we are touching upon Bishop effective stresses and the 2 independent stress measures. Then I'm talking about soil suction, soil water characteristic curve. I'm introducing also groundwater flow in unsaturated soils. And then the main focus is on unsaturated slope stability. Moving to the coursework itself, it's kind of real natural silt slope in Sweden, where we have almost full data, in terms of cross-section, detailed geometry, cone penetration test data for the students to use, natural water content profile, bulk density, grain size distribution. But the most important thing about that we have indeed some measurement for the soil water characteristic curve at a different depth, which is not really available usually. So that was provided also for the student. And on top of that, we have some real precipitation data to be, for 1 full year, to be used as, and applied by the student as infiltration and to check on the stability of the slope. They have also some missing data to be estimated, like saturated hydraulic conductivity. Now, about the used methodology, the student uses software called GeoStudio. It's a very famous one, well-known. And basically, they are using two modules, slope W and seep W. Why we choose this one? Because it has the possibility to incorporate suction in the calculations. And then they are asked to repeat the calculations in two scenarios. The first one by neglecting suction. I would call it like classical approach, putting it to 0. And now we have a lot of lecture about this one. And then we have another scenario focusing on including the effect of suction, where the slope is subjected to infiltration, the real data that we have. And they have to use the measured data for soil water characteristic curve to derive the parameters for soil water characteristic curve model that they are going to use. In this case was Van Genochten and then Friedrichsing. And they have a third trial that they try to estimate the soil water characteristic curve in absence of any data based on the grain size distribution. At last, they are employing two different criteria, should speak, or two different relationships between suction and the increase of apparent cohesion, one called linear relation. So they have this tangent phi multiplied by suction, and then the nonlinear one where we incorporate the soil water characteristic curve. Now looking to the student results for the first scenario, when they neglect the suction, most of the groups, they calculated a safety factor below 1, indicating a like failing slope. However, it's in reality, it's not failing. So it's standing there. So this is the first intended outcome, like learning outcome, satisfied that they're predicting something is failing, but still standing there. So they need to think why it is still stable. However, even though they are ending with this value, they're still predicting different value from one group to the other, and that relates to the variability in estimating the layering, the geometry that they have, and some missing data that they are using. Now, for the second scenario, here you see one example. They have plenty of results, but this is some example. For the first one on the left, you see the predicted factor of safety over time by different groups. And I forgot to say that those groups, each group has 3 students. And you can see most of them like predicted a variation in safety factor as like function of the variation of suction, of course. And then for the other one on the left, you can see a prediction by a same group, but when they employ different models for the soil water characteristic curve. And you can see also here some variability in the results when they employ different soil water characteristic curve models. Now for the educational impact, and I think this the first one is the first and second one is the most important one, that the students realize that in partially saturated soil, we don't have one single value for the safety factor, while it is, in fact, a dynamic value that is changing with the changes of suction. And I always stress it's not only about the safety factor itself, but it's also about the time to failure. And that's something that we can predict with the variation of suction. Maybe the fully saturated soil is the most like conservative one, so to speak, but it could fail when we still have some suction there. And the time to failure is very important. And then the students recognize the role of the assumption related to the soil water characteristic curve. Also, they realize the realistic behavior of slope when you incorporate suction. And finally, they also understand the variability relates to, when you predict the safety factor relates to the assumption that you do in terms of soil layering, soil water characteristic curve, and missing data. Now, as conclusion, future direction, I think I said a lot about the first one, that integrating suction is important. Like if you want to predict realistic behavior of the soil, then the soil water characteristic curve is extremely important also. But for future exploration, and I here thank the reviewer for highlighting this one, that maybe I need also to include something relates to the variability in the estimation of soil strengths based on CBT test when it is in unsaturated conditions, Also, I have to include some insight into the role of hydraulic conductivity function and emphasizing also the historic behavior of the soil water characteristic. Finally, I would say this course was offered 3 years ago, and we constantly get an excellent feedback from the student for the organization of the course and also for the clear learning outcomes and constructive alignments. Finally, I would like to thank the Chalmers students for providing the data for this talk and also for the 2 reviewers for the excellent comments that they provided for this paper. And thank you, of course, for your work.
We do have time for a few questions. Marina, first.
Yes.
Yeah.
I'm just curious, in what context you were able to get this data for the slope, the CPT data and all that you were saying?
I mean, it relates to one PhD thesis that was carried out in Chalmers there, and there we have the full set of data that we used it in our course.
Yeah, question?
Thank you very much for your talk. I really enjoyed the topic, and I think I'm going to adapt a couple of those things into my courses. I do have one question and maybe one suggestion.
Yes.
I also teach factor of safety concept, even though Eurocode 7 doesn't allow this approach, right? How do you justify factor of safety concept teaching?
In which sense you mean? Like,
when for doing a slope calculation,
yes.
According to Eurocode 7, you will have to use a different approach. So factor of safety is not allowed anymore.
Well,
so you have,
in our
Sweden
case,
it is.
In this case, I am just using the total, so to speak, the total safety factor. So I am not employing any partial safety factors here. And please, just to remember always that I am trying to introduce the concept. So it's always like to highlight the effect of suction, and that's the main focus. Now for the details, and even I'm using here, they are using the LEM equilibrium method. So it could be like if you go for finite element and so on, it could be, but that's what we are using at least. So the total safety factor.
I see. And this is where my suggestion kicks in. Yeah. If I remember right, your perception data were from 1995, so the rainfall data
yes,
you had?
Yeah, the rainfall.
So it's over 30 years old data. Yeah. Maybe a suggestion was to implement some climate change rainfall data. Yeah. And I suppose
in fact, this is one idea for the PhD
a lot of changes with the slope stability.
Like now, yeah.
One final
but
comment.
Thank you very much.
Alessandro?
Yeah.
Sorry, I'm doing the same, so I'm I'm taking the liberty to answer. So that factor of safety is not the partial safety factor. It's the ratio between destabilizing and stabilizing moments. Now, it might be that GeoStudio has that option to calculate as a reduction factor according to the Eurocode, if you are going to that story. Off the record, the reason you are applying the partial safety factor to the friction is because you're assuming that the major source of uncertainty is coming from the quantification of the soil shear strength. Here, the less important thing is the shear strength of the soil. You have much more uncertainty on the hydraulic conductivity of the material. He's inventing it, and everybody's inventing it because the hydraulic conductivity is invented. He's inventing the rainfall, or the rainfall might be fine because you can go for rainfall with a certain return period, but there is the historical, so it's not the rainfall that is triggering the event, it's the antecedent rainfall. What do you apply what is the statistical antecedent rainfall 1 year before with the return period of 10 years, God knows. Third, there is the evapotranspiration story, and God knows. So if we want to claim that we are designing according to the Eurocode, we can plug a number and we can go for the partial safety factor to be formally consistent. But the reality that we are placing the uncertainty on the less uncertain thing that we have.
Thank you for the comment, and then I would leave the discussion for later if we want. Thank you very much.
Yeah.
And next is the last presentation of this session. We have Nuria Pinyol with a contribution on teaching unsaturated seepage and wetting collapse coupled modeling.
Hello, good afternoon. I'm going to present how we prepared a class to teach the modeling of the coupling of the mechanical and hydraulical behavior of unsaturated soils. Generally speaking, a course of unsaturated soils is outlined as follows. First, basic and fundamental concepts are introduced, theoretical framework, soil response under loading, wetting and drying, experimental tools and experimental behavior, constitutive modeling for mechanical and hydraulical behavior, and finally, the modeling of a real case if it's possible, usually numerically. And what we observe is that even going deeply and going inside to these topics, there was a gap in the current understanding of the students to know how to integrate all relevant concepts and how to account for flow mechanical interaction within comprehensive modeling frameworks. And then we prepare a class for master students to integrate the flow mechanical interaction into a non-saturated boundary problem, developing the analysis step by step with the aim that the students can follow everything without using closed programs, closed numerical programs that usually, or that there is the risk that students use as a black box programs without understanding what the program do or what that program does. And then the point is that we use simple mechanical and hydraulic constitutive laws to enable analytical integration or simple numerical procedures. Then we solve a real case in order to motivate the students, because you know forensic engineering is always motivating. And this is the case. I show you the class very briefly because it is 3 hours, sometimes 4 hours class. This is an embankment of a bridge at Budman. This embankment exhibited excessive displacement during relatively intensive rainfall period after some months of this construction. And at the first sight, it could seem a landslide because of the scar, but not. It deformed volumetrically. You can see clearly in this figure. At the beginning, the embankment was here, and you can see the vertical and the horizontal displacements, indicating the volumetric compressive behavior of the embankment constituted by a low plasticity sandy clay during the wetting. This is the gap that was observed. It doesn't work anymore. This is the gap that it was observed that was filled by a sun immediately after the rainfall. Then the aims of the class is to answer the questions asked by the road authority, identify the causes for the damage suffered by the recently built road, and determine if future rainfalls of similar or higher intensity would induce additional damage to the embankment. And then we describe the soil with the properties, with the compacted conditions. All the specimens compacted on the field satisfy the dry density specified, but they were compacted at dry conditions. And also we have some tests carried out on the laboratory, an odometric test, including saturation and also the water retention curve. Then, at that moment, we introduced mechanical constitutive modeling relating the stress variables, in this case a net stress and the suction with strains. We do not include the coupling, in the sense we do not include here the degree of saturation. And we explain to the students a mini BBM, a simplified Barcelona basic model, and in order to explain a constitutive model in terms of, in the framework of elastoplasticity, to interpret the collapse and the loading. And we formulate this model introducing the yielding loading collapse, but as you can see here, this curve is easier than the BBM, if you know the model, because it's just an exponential curve that is mathematically easier to integrate, and we have the same hardening rule, but we remove the elastic part, it's not relevant. And then with these formulas, we can calculate the plastic deformation during loading and wetting, and explicitly, analytically. And the students can calculate the magnitude of deformations when the net stress, the mean net stress increases or the suctions changes. But the point is, okay, even understanding this constitutive model, what we do with that, because the problem is that we have to solve this embankment. The approach of the problem is simplified in the sense that we only analyze the central column under odometric conditions. The question is, calculate these displacements. This is the integration of the plastic volumetric strains, but how we calculate the magnitude of the changes in stress and change in suction when the rainfall appears or the water table rise. And usually it is done by a model, and the point is that they have to solve analytically or simple numerically. And then we explain that in unsaturated deformable porous soil, changes in suction may depends on the water flow, the change in retention capacity, and the change in volume of the soil skeleton and solid and water particles if they assume compressible. And then we establish the soil and water mass balance equations, and they are defined step by step from the beginning as continuum mechanics. And we establish all the questions and the hypotheses, and finally we get this mass balance equation for the porous media, describing that the water in the soil depends on the storage water by varying the degree of saturation, the formation of the skeleton, or the flow. And then at this point, we need to express these variations in terms of our variables, which is the suctions and the net stress. And then we do that by step by step. The degree of saturation is obtained by the water retention curve that we use, the Van Newton, which is directly depending on the suction. We don't introduce here the effect of the void ratio, in order to not make too complex the procedure. And we have these equations. Later, we introduce the generalized Darcy law in odometric conditions. And again, we have this term in terms of suction variation. And here we introduce the relative permeability. All of these concepts are known for them. And finally, here, the volumetric deformation, which, and we recover the constitutive model presented before. And finally, these equations is now developed with the derivative to this one that can be solved by backward finite differences, and here able to calculate the variation of the suction in any time and in any point of this column of the embankment. And now they are able to solve the problem, and they do that with the parameters of the real problem. And finally, they calculate the settlements and the evolution of the suction in time for the first wetting or for subsequent eventual wetting. And the class also include conclusion, discussion, learning lessons, and mitigation measurements. And okay, as final remarks, this work, I think, that provides an intermediate but powerful approach that isolates the fundamental physical aspects for analyzing the wetting collapse of a hydrometric column, disregarding secondary sophistications. That is important, because otherwise they cannot, the students cannot go forward. The simplicity helps to the students to follow the developments step by step, because they can do everything by own. And the class also demonstrates how the tools and concepts learned before of this course, like how to do an integration, how to do the find a difference by hand, or these kind of things that they learn in other courses at the beginning of the degree are useful to solve a real case. And they are happy to know that, usually. And it also adds some geotechnical lessons, obviously. Compaction on dry sites leads to a risk of collapse, even reaching the achieved density. Collapse strengths are essentially irreversible, and capillary rise from shallow water should be accounted for in rainfall-induced wetting. And thank you for your attention.
We do have time for one question, maybe a second quick one. Is there any? One, go ahead.
Thank you for the presentation. I have a question regarding the hydraulic side of things. So can you clarify the hydraulic conductivity function that you used and how you considered evapotranspiration? Because those are big unknowns in this type of problems. Yeah.
Okay, the relative permeability, we always use this one, that the permeability is reduced with the degree of saturation, and the parameter M is always 3, because this is a magic number. We always put 3, and it is good enough. Sometimes I put 5 in some papers because 3 was not enough good. But we don't have data. We have data about the water retention curve in this part, with only for high degree of saturations, which is the relevant part for our model, but nothing about permeability. And we do not include evaporation. We put we simulate the rainfall like a ponded water. Like there is enough water to make possible to introduce the water into the soil with pore water pressure equal to 1, and there is no accumulation of water. Then the water can run off. That's it.
Thank you. Any other quick question? Last one, Alessandro. I'll wait for the mic. Wait for the mic.
So they're using the finite difference for both the constitutive model and the boundary value problem?
No,
that's what I missed.
The constitutive model is solved completely analytically.
Okay.
It is here, the constitutive model is solved analytically. Then you can calculate the deformations with the changes of...
Okay, but then when they solve the boundary value problem, then that's the finite difference, or you're using...
Exactly. When you introduce all of these equations in that equation...
Yes, okay, so there's a boundary...
Here, yeah, here you have the suction, the time integration.
Okay, so this is what they do manually, with the finite difference. So they are not using an existing finite element, but they do it from scratch.
Yes, because you cannot integrate. Okay, I cannot learn to the students in just a moment the integration in finite
it's
element. But
good.
this is,
No,
this is the integration in time and in space for Darcy, that it's enough. And it is explicitly and it is perfectly reached.
Thank you.
Thank you very much. Just very curious, how long does it take in class time, the theory, and how much time are they given to?
It takes 3 hours, but the students has already done the course on unsaturated soils given by Enrique in the same semester. Then is the last class of this course.
Of that class, of that course. Okay.
Yes.
Thank you very much. So I thank all the speakers of our unsaturated special priority team. And without any break, I leave the floor to Alberto Ledesma for the final session. Thank you very much to all, also for the lively discussion.